Hello my dear friends, hope all of you are doing well. Please do maintain all the COVID protocols seriously. So today I will start discussion with the idea of the cell, what is the electromotive force or the EMF inside the cell, and also on the cell's internal resistance. So without any further delay, let's start. So our topic of discussion will be for today, cell, its EMF and the internal resistance. So we have already made the discussion that we need to find a source for the steady current in the electrical circuit, which can be provided by the electrical cell. So the electrical cell is there to find the steady current in the circuit. So now the cell has the two electrodes, the electrical cell, you can see from the figure. One is the positive electrode, one is the negative electrode. So it is positive electrode is marked here as capital P and the negative electrode is marked here as capital N. So you can see both the electrodes are dipped in the electrolyte solution, and the positive electrode has the potential of V plus, where V plus is greater than 0 between itself and the electrolyte solution, and where the negative electrode has the potential of minus of V minus, where V minus is greater than or equal to 0. It is also the same between itself and the electrolyte solution. So now when there is no current, there is no connection with the wire between the two electrodes, positive and the negative one, the electrolyte has the same potential throughout. So what it will be, V plus minus of minus V minus, that V plus plus of V minus. So this is called the electromotive force or the EMF of the cell. So I have written here it's like epsilon is equal to V plus plus of V minus, that is greater than 0. So basically you can understand that the epsilon, that is the electromotive force or the EMF, represents a potential difference and not a force. Now if we connect a resistor R, you can see from the figure I have connected one resistor R with the two electrodes, the positive and the negative one. So a current I will flow, you can see this is the direction of the current from C to D and also through the electrolyte. So in the external wire the current will flow from C to D, and in the medium, in the electrolyte solution, the current will flow from B to A. So now if I write that if we consider that the electrolyte solution has a finite resistance of small r, it is called the internal resistance of the electrolyte. So now if in the external circuit there is a resistance, that is the capital R, you can see from the figure this is the capital R. If it is infinite, so the current will be what it will be, I is equal to V over R. So that means the I approaches to 0, where V is the potential difference between the point P and the N. You can see from the figure, the V is the potential difference between this point, this is the positive electrode and the negative electrode. So in between the potential difference is V, capital V. So I can write it like the capital V is equal to potential difference between P and A. So again you can see from the figure, this is the P and A, both are the same on the same material, so it has the 0 potential difference in between, plus potential difference between A and B, plus potential difference between B and N. So V is equal to potential difference between P and A plus potential difference between A and B plus potential difference between B and N. So the first term and the third term is 0. So only the potential difference between A and B, that is the electromotive force. So V is equal to V plus plus of V minus is equal to epsilon. So I have already discussed that epsilon is equal to electromotive force is equal to greater than 0. So however, if we assume that the external resistance is R is not infinite, it has a finite value, then I is not equal to 0, and the potential difference between P and N, what it will be, V is equal to V plus plus of V minus minus of IR, where I is the external flowing current in the circuit, R is the internal resistance of the electrolyte. So it becomes, I have written that V plus plus of V minus as epsilon minus of IR. So you can see that the negative sign comes as the current is flow from B to A. So you can see from the figure that in the external circuit this is the direction of the current from C to D, and internally in the electrolyte solution the current is flowing from B to A. So now normally in the practical calculation we don't consider the internal resistance value of the electrolyte, that is a small r. So now if epsilon, the electromotive force, is very greater than IR, so the internal resistance of the electrolyte can be neglected. So now if V the potential difference across the capital R, the same in between P and N. So we can write that V is equal to IR from the Ohm's law. If I put this in the expression of V is equal to epsilon minus IR, so it becomes I times capital R is equal to epsilon minus I times small r. So there I will get the expression for capital I, the current in the external circuit, I is equal to epsilon by R plus R. So the maximum value of the I, what it will be, I max is equal to epsilon by R, where when this R, the external resistance in this circuit, you can see in this circuit is 0. So when the external resistance is 0, the I reaches maximum value. So I max is equal to epsilon by R when capital R is equal to 0. But normally the maximum current is much less than epsilon by small r, because to prevent the permanent damage of the cell. So now we will discuss when more than one cells are connected together in series or in either parallel combination. So the cells in series or in parallel combination. So first we will consider the series situation. You can see from the figure here, this is the two cells having this EMF value of epsilon 1 and epsilon 2 and having the internal resistance value of R1 and R2. They are connected in series. Series means that the one cell positive terminal will be connected to the next one negative terminal. So we consider that the potential of the point A, B, C, let VA, VB and VC. So we can write it VAB this is the potential difference between the point A and B. VA minus VB is equal to epsilon 1 minus I times R1. Similarly, VBC, the potential difference between B and C, what it will be? VB minus VC is equal to epsilon 2 minus I times R2. So now I want to calculate the potential difference between A and point C. So VAC is equal to VA minus VC is equal to VA minus VB plus VB minus of VC. So it becomes epsilon 1 plus epsilon 2 minus I times R1 plus R2. So now this is the equivalent circuit you can see from the series combination of the two cells in series. So this is the epsilon equivalent is the equivalent EMF. This is the R equivalent is the equivalent internal resistance of the two cells connected in series. So we can write VAC is equal to epsilon equivalent minus of I times R equivalent. So if we compare this VAC and VAC here, we can see that the epsilon equivalent becomes epsilon 1 plus epsilon 2 and R equivalent is equal to R1 plus R2. So we can see that the equivalent EMF is the sum of the individual EMFs and the internal resistances will also add up. So now you can see from this figure, this is also one kind of series combination where this is, but here the two negative terminals of the cell next to each another are connected in combination. So in this case, epsilon equivalent, what it will be? Epsilon 1 minus epsilon 2. It means the difference of the two EMFs, because the VBC we need to write as minus epsilon 2 minus of IR2, because with the direction of the current the sign will change. So now for the parallel combination, you can see from the figure here, this the 2 endpoints of the two cells are connected together. So one is epsilon 1 R1, the two parameter values, another one is epsilon 2 R2. So here the current will add up. It means I is equal to I1 plus I2. So for these 2 points B1 and B2, the potential are the same. So this is the equivalent circuit. Epsilon equivalent is the equivalent EMF for the two cells in parallel combination, and R equivalent is the equivalent internal resistance. So from the calculation we can see that V is equal to VB1 minus VB2, the difference of the point VB1 minus VB2. So in each case the V will be epsilon 1 minus I1 R1 is equal to epsilon 2 minus I2 R2. So the main principle is that I will add up. I is equal to I1 plus I2. So if I put the value of I1, substitute the I1 in terms of epsilon 1 and V, so it becomes epsilon 1 minus V by R1 plus similarly I2 will be epsilon 2 minus V by R2. If I collect it together, it becomes epsilon 1 by R1 plus epsilon 2 by R2 minus V times 1 by R1 plus 1 by R2. So now we can write it like V times 1 by R1 plus 1 by R2 is equal to epsilon 1 by R1 plus epsilon 2 by R2 minus of I. So if I replace V, what it will be? V is equal to epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2 minus I times R1 R2 divided by R1 plus R2. So it becomes epsilon equivalent minus I times R equivalent. Therefore the epsilon equivalent is equal to, we can compare these two. So epsilon equivalent will be epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2, and R equivalent will be R1 R2 divided by R1 plus R2. So now for the n cells in parallel combination, we can write that the equivalent resistance 1 over R equivalent, the total internal resistance is equal to 1 by R1 plus 1 by R2 up to 1 by Rn. So this will add up. And similarly, we can write the equivalent EMF, what it will be? Epsilon equivalent divided by R equivalent. We can write it like epsilon 1 by R1 plus epsilon 2 by R2 up to epsilon n by Rn. So we need to add up all these things also. So my friends, I am concluding my discussion here. If you are new on this channel, please do like, share and subscribe Invisible Threads. Stay tuned and keep supporting. Thank you.